Okay, today we're going to talk about Ancova. So what can Ancova do? Well, Ancova can talk about whether our dependent variable, the means of that dependent variable, are equal across levels of an IV. And what we're going to do is we're going to control for effects of another continuous variable, in this case our CV, which is a covariate. So why would you do that when you want to, or when you want to control for these noise variables, these confounding variables that can't possibly interrupt your different levels of the IV. How does it work? Well, a very basic description of it is that it breaks down the variance into variance because of the IV, residual variance, in various explained by the CV, so we can get a more accurate picture of what's going on while controlling for the CV. So before we do anything, I just wanted to talk about the assumptions briefly. There are four major assumptions of running an Ancova, and those are linearity of regression, homogeneity of error variance, independence of error terms, and homogeneity of regression slopes. So you're going to want to check all of those during the process of running your Ancova. Okay, so now we're going to briefly talk about my research topic. So let's say we have an intelligence test, and we have scores on that test, but we want to control for a covariate, which in our case is conscientiousness, because maybe the literature has pointed us in that direction, that conscientiousness can have a confounding effect on our two variables. So we're going to control for that by including that into our analysis here today. So first we're going to begin with our syntax here, and it's all prepared. So we're going to start by bringing multiple packages that are needed. Well, we have 12 warnings there. We're just going to ignore that. No. So we're going to bring all these packages in, and the library function is essentially loading these packages so we're able to use them. So there we go here. And now what we're going to do is we're going to import our data set. And this data set is an Excel file. There you are. We're going to bring that in. We're just going to give it a quick look over, and I pre-formatted it so that my condition here is a numerical variable instead of a categorical name variable. And here's our code that brings that in. Okay, and part of my code here was view, and that's going to bring my data here into a different window so we can observe that, and it's also been loaded into my environment. So now we're going to start. We're just going to run a little box plot here just to get a visual of what's going on. This looks a little wonky here because I only have 3 conditions, so they're labeled there. But as you can see, just visualizing it here, there's a very small range in my conscientiousness scores. I'm not sure why it didn't pop up there. It could be too large. But as you can see, that just from eyesight, we can see there's a major difference between those things. So what we're going to do here in this line is we're going to push. This is the push symbol. This code here into condition v2 is going to be a new variable that will pop up into our environment here. So what we're doing is we're identifying our data here, the name of our data, then the condition. The condition is our independent variable that we're going to specify, and we have the factor function here, so this is going to factor that. We have 3 levels in it, so we're going to create a list. The C function creates a list, 1 to 3, and the labels of that list are Waste, Raven, and Woodcock, 3 different intelligence testing batteries that we're going to measure here. Ordered equals true, and this creates a factor called condition 2. As you can see, it pops up there under values. And now what we're going to do is we're going to create a data frame. We have a data frame function, and we're specifying the manipulation we just did, and this is going to create a new data set. So we're going to see this data set now, and these should be factored into Waste, Raven. As you can see, our labels resulted there. And this is our condition, which is our independent variable with 3 levels. And a good measure of thumb to see whether you have actually factored what you're attempting to, because I had some issues earlier, you kind of hover over this name here, and it says column 1 factor with 3 levels, and that's what we want to see. And now here are the changed names of my variables. I could have made them something more simple for argument's sake, but regardless. Okay, now we're going to do some summary statistics. The by function produces those, and we're going to run these again. And these are just so you can get a different picture of what's going on with yours. Something you would want to look at the beginning is the change in your means over your different levels and how those can be manipulated by your covariate. But you can't really make any large assumptions according to your data by running that. And so our next line 20 here, we're going to check for the homogeneity of variance, and we're going to do that by operating Levene's test. Here we're specifying our new data set, and here we're specifying the outcome variable, as well as condition, which is our factor. Center equals median. This function here, essentially, instead of using mean as our measure of central tendency, we're using median because it's a more robust measure and it cannot be skewed as much by outliers. So we're going to run that. We're going to look at our p-value here, and our p-value is not significant. So that says that we have not violated that assumption. So now here we're going to create an Ancova model. We have the traditional ANOVA set up here with our independent and dependent variable, or predictor and outcome variables, and we're going to push that in the test model. The only addition here is we're adding, the plus sign here, we're adding our covariate to control for that. And now I'm specifying data set 2 by saying data equals. So we're going to run that, and that produces an output, and now we're going to summarize that output using the summary function, and that shows us what's going on here. As you can see, we have not achieved significance. Our f values are fairly small. We have not achieved significance, but regardless, we're going to go on. And now we're going to create a new model. And just to indicate that order does matter when we're doing things, it does not produce the same output according to the way R reads our syntax. So we're going to create a new model with the covariate first, just to kind of check out what that manipulation does. And that produces new output, and we're going to summarize that to view it. Here again, we do not have any significance. And again, we're just going to run another ANOVA with a different function. The AOV and ANOVA functions, capital A, do different things, but this time we're going to run type 3 sum of squares. But for my purposes here, I'm more interested in the type 2 sum of squares because I realize, pre-existing looking from the data, I do not have an interaction effect. So different types would be more conducive to that, to looking at interactions and things like that, but I'm more concerned with the type 2 sum of squares, the main effect, so I'm going to run that. So we have our output here, and now we're going to move on. So one thing we have to do while running an Ancova is we're going to have to adjust the means because of the effect of the covariates. What we're going to do is we're going to essentially adjust those means into a new thing called object here, and then we're going to summarize that, and we can look at the manipulated means in our output. We just summarize that. So now what we're going to do is this function here, SE, we're going to want to tell R that we would like to see the standard error. Okay, and now we just produced. It seems I have an error in my syntax. Okay, we produced test model there. So I apologize for that pause. But as we look at our coefficients here, we have not achieved any significance on any of the levels. And this function here essentially summarizes that in the context of a linear model. So now what we're going to do is, even though we do not have we have not achieved significance between any levels or from the effect of the covariate, we're still going to run a contrast here. So we're going to have our first variable called contrast 1, and this is going to create a list of weights for our contrast according to the levels. So we have three different levels of the factor. So I will talk about that in a second once we're able to visualize that. So contrast 1, list of -2, 1, and 1. These are assigned weights according to the pre-established list of the levels of my factor. So now we're going to create contrast 2, 0, -1, and 1, and these are not arbitrary assignments of the numbers, but I will talk about them in a second. So now we're going to take the sequences of the arguments that we have created here in this line, and we're going to combine them. So now we can view our weighting here, and as I talked about, this is not an arbitrary assigning of the weights. So we're going to look at this, -2, 1, and 1. And the biggest thing here is there's a couple rules of thumb. The first one is that we're going to contrast the negative and the positive levels. So as you can see here in this level, we're contrasting waste with the raven and the woodcock combined into one group. So the biggest thing here is you want each column for that matter, to add up to 0. So as you can see, 2 plus negative 2, that's 0. So we're not violating that assumption. And here in contrast 2, this signifies that we're not going to look at this variable here because it was individually contrast in the first one. So we're going to compare raven and woodcock levels 2 and 3. So negative 1 and 1. And this is exactly what we want to see. They all add up to 0. And in the first contrast, we compared these to those. And in the second contrast, we're going to omit that because of that and compare these two levels. Okay, so let's move on. Where are we here? So now now that we have our contrast, so we're gonna create a new model in the same exact way we did earlier. We're gonna call that model test contrast. So from there, we're gonna view our significance levels. And again, we don't have any significance in our contrast, and that's as expected because we have not found significance when we did more broader specifications. So here's our first contrast and our second one, and if you ever forget what you're looking at, you can always reference back to your contrast here, again, negative versus positive. Okay, and now the HORS function, HORS, homogeneity of regression slopes. So as stated earlier, that is an assumption of Ancova. So we're going to double check that. And we're going to bring that out down here and summarize that. And according to our data, we have not violated that assumption. Okay, on to line 52. So now we're going to want to look at the effect size. And to do that, we're going to create our own function to look at partial eta squared. So we're going to specify the function and call it our contrast. And we're going to use the function, and we're going to have these two values, t and df, and we'll specify what those mean earlier. And here, I took out from Andy Field's R a function here. And essentially what this is doing is we're going to create a mathematical equation with these placeholders, t squared divided by t squared plus df, degrees of freedom. And we're going to push that into R. And then we're going to print and paste what our R value is going to be. So that's going to create an output for that. So let's run these things. So now we have created our function, and this is going to create a list of what to plug into this function up here with the placeholders according to these respectively. So again, the C function creates a list, and that's a list of our t's, which was obtained from an output earlier. And now we're going to plug in that it wants to read df is 26, so these will be plugged into the t values, and this will be plugged into degrees of freedom. And then we're going to run that function. So here are our effect sizes here, and they're fairly small, 0.06 and 0.13.